All right. So, good morning. What we saw yesterday was, I talked about the importance of I tried to tell you the distinction between four different types of structures: the macrostructure, the microstructure, crystal structure, and atomic structure. Well, the three listed at the bottom are important, but microstructure is some kind of an additional information that you get when you're dealing with materials, thin films, single crystals. But we need to attach a lot of more importance to crystal structure and atomic structure. And it ends, of course, it doesn't end just by getting information about the crystal structure and atomic structure. And the next step is to do physical property studies. When I give some real examples of how to ascertain the bulk part that I'm showing here, I'm calling it a crystal. Of course, we need to do crystallography and ascertain that it's a crystal. So X-ray diffraction is a very useful tool that way, but it's not the only tool. Again, you also have other high-end tools which normally have to be used in order to unequivocally prove that a crystal is indeed a crystal. Okay. An experiment like Rutherford backscattering and channeling experiment. But then such experiments are not available in plenty. So you only have specific places where, you have to book the beamline, you have to write a small proposal for that. But then on a regular basis, if you're looking for crystallography experiments, today you have X-ray diffractometers almost in every department in a place like IIT. And sometimes departments have two X-ray machines. And one X-ray machine for single crystal, one for thin films, one for powders. You can also divide X-ray diffractometers that way. And atomic structure assessment, you have many techniques, spectroscopy techniques, you have X-ray photoelectron spectroscopy, which is again it's a high-end technique. You normally have it as a common facility. You have Raman spectrometer. Raman spectrometers are very common in materials labs, and so on. So it's a combination of the understanding of atomic structure and crystal structure that will make a given study on polycrystalline systems, single crystals, amorphous materials, thin films, and all these various forms become complete. Okay. So starting with polycrystalline bulk materials. So polycrystalline, why I given bulk in brackets is that's a reference now, because the same polycrystalline material can also be obtained in nanoform. So since you have the nanoform on the other side, where you have a science that deals with what happens to the physical properties of these bulk materials when they're obtained in the nanoform. So for clarity, nanoscience is a science that deals with entities that are within 1 to 100 nanometers. I also mentioned that bulk properties of material systems, like specific heat, thermal conductivity, electrical conductivity, even reflectivity, band gap is also a bulk property. You don't expect these bulk properties to change, right? Example is again a big copper block, a small copper block, and a very small copper block, or a long copper wire, 1 meter long, half a meter long, 1/4 of a meter long. What changes is the resistance in these three cases, but the specific resistance, that is resistivity, will not change. That's a bulk property. But when you go down to the nanoscale, 1 to 100 nanometers, most of the materials, semiconductors and metals, they start showing these interesting changes when you hit the nano window of 1 to 100 nanometers. That's a course that deals with nanomaterials, why the physical properties change, all that you learn there. So in simple words, why the physical properties change is because of the quantum effects that you bring in. The quantum effects that are set in when the bulk material is brought down in size to those nanoscale levels of 1 to 100 nanometers. I've already given you an example of thin film with a thickness of less than 100 nanometers. Is an example of one of the nanosystems. It's a 2D nanomaterial. And today we talk about ultra thin films, where the thickness of the layer could be one monolayer, one unit cell thickness. I also mentioned that the one-dimensional nano rods or nano strips can also be obtained using thin film growth methods. These are all interesting things that you'll see how to realize. If you start with polycrystalline bulk material, of course, a polycrystalline bulk material is required if you want to grow thin films using a certain method. Remember, I also told you if you're dealing with thermal evaporation, first I said physical vapor deposition requires solid or molten sources. That means I take a piece of metal, a bulk part of a metal, either in the form of a powder or an ingot or a small piece, and just melt it. But I said the same physical vapor deposition, the second method, which is sputtering, I'll go into the details of sputtering later. It requires the material in a bulk form. I said you need the material in the form of a 2 or 3 inch cylinder with, of course, very small thickness. So it's a circular disc with a small thickness. You need that. So how do you get it? Polycrystalline materials, as I showed you, normally a ceramic is obtained in a powder form, and these powders have to be compacted under high pressure, and these compacts are then heated. That's called the process of sintering. So during the process of sintering, what happens is the individual particles coalesce, right? The nucleation happens, they all start coalescing, and that process of coalescence leading to the formation of a bulk polycrystalline material leads to the existence of grains and grain boundaries. Grains and grain boundaries are inevitable in the case of a polycrystalline system. I also mentioned that the whole process of thin film growth is to get rid of these grain boundaries. Same is the case with single crystals. So the processes that are used to get thin films, polycrystals, and single crystals are all different. Then the definition of a single crystal is, well, I can convert this polycrystalline material into a single crystal if I make the polycrystalline powder or bulk through the process of single crystal growth. Right? There again, like PVD and CVD techniques, you have several thin film single crystal growth techniques available. One famous technique is called the Bridgman technique. Another famous technique is called the Czochralski technique. It's a Czochralski technique that is used to grow these large balls of silicon crystals from which silicon wafers are cut for device fabrication. You have flux growth method, you have hydrothermal method, your Chiropoulos method. There's so many single crystal growth methods. And thin film growth methods, I broadly said the categories are PVD and CVD. We'll see some of the methods in each category. So a single crystal basically is a bulk material where, of course, there are no grain boundaries. It's a perfect periodic order in 3 dimensions. So that means the unit cell at one end of the, if I call it a single crystal, that means the unit cell here and the unit cell there are correlated in the sense that there's a perfect periodicity of unit cells from this point to all 3 dimensions. That is a single crystal. That means the long range order exists in a single crystal. In a polycrystalline material, that long range order is not there, but long range order exists to the point where the crystallinity is. That means a grain. I've shown you a picture of, I'll show it again, a grain, another grain. So within the grain, within a grain, you have single crystalline arrangement of unit cells. That means there's a perfect periodicity within the grain. Grains, if you recall the picture that I showed you yesterday, the sizes vary anywhere from 1 to 50 microns. So within that 1 or 10 or 50 microns, you have perfect periodicity of all these unit cells. But then there's a break in periodicity in the form of a grain boundary. Then on the other side, you have a periodic formation of the unit cells, which you call it another grains, right? So you have an ensemble of crystallites. That's why the name polycrystallines is. But here, it's only a single grain. So to declare that a material is single crystal, you need to do several tests, of course. But then once you know that a system is single crystalline, there is a perfect periodicity in the 3 dimensions in the entire volume of that material. Thin films, again, you want a thin film to be highly crystalline. You want to have high degree of crystallinity in a thin film also. A thin film which is as good as a single crystal, that means a perfect period. See, what is the difference between a single crystal and a thin film? A single crystal is a bulk system, right? It is standalone. But a thin film is deposited on a substrate. There's a base material on which the thin film is deposited. That means all the unit cells are supported by a base material. The base material plays a very important role. I mentioned that. So even though you get large areas of thin films, the thickness is always limited. You can't have a thin film grown to these thicknesses, right? So that's the main difference. So over, say, 1 inch square of substrate, if you get half a micron of thickness of the material, and over this given area of 1 inch square and half a micron thick, if there is a perfect periodic order, like in the case of a single crystal, those thin films are called epitaxial thin films. So epitaxy is a term used to describe the single crystal nature of thin films. Always remember. So you come across a term epitaxy, that means it is a single crystalline thin film. So one of the physical vapor deposition techniques is called molecular beam epitaxy. So the name itself suggests that if you use that method for certain category of materials, you end up getting an epitaxial single crystalline thin film. So unlike in the case of a single crystal is a single crystal, a polycrystal is a polycrystal. But when you come to thin films, you can have single crystalline thin films, right, which are epitaxial films. You also can have polycrystalline nature of the films. It depends on the conditions of the growth. You can have a completely non-crystalline form of thin film, amorphous. You can have textured thin films. You can have oriented thin films. You have highly oriented thin films. You see how many different categories of the same material can be obtained, because thin film growth, as I told you, depends on pressure, temperature, and substrate. 3 variants, right? So if any of these things are not chosen properly, instead of getting an epitaxial growth, you might end up getting a textured growth or oriented growth or a polycrystalline growth. And in thin film terms, highly oriented growth is also known as, well, you can almost equate highly oriented growth to epitaxial growth, right? So look, now so as we go along, you'll get to see how thin films are grown. Then the biggest challenge is to find out which of these forms a thin film belongs to. Of course, the straightforward answer is X-ray crystallography. It'll tell you, it'll distinguish between all these different types. When you come to this highly oriented one, if you can bring in one or two additional more sophisticated techniques, then you're sure that you have an epitaxial thin film. Okay, yeah. So a basic building block, unit cell, and another example of a little complex unit cell, and this is what is meant by perfect periodicity, where you see atoms arranged in a perfect periodic way. That's what is meant by long range order. You see the way this set of atoms are arranged, you'll see the same thing on the other side, on the extreme side also, without any crystallographic misorientations or breaks and having the dislocations and other crystallographic defects. So crystalline system, you see perfect periodicity. Polycrystallinity, the periodicity is there in small pockets. Again, going back to the example of, so you take any bulk material, polycrystalline ceramic bulk material, which you obtain from powders, compaction, heating, and if you put it under a microscope, to the naked eye, you can't see all this because, you see the scale here. These grain sizes are varying from 1 to 50 microns. So we don't have, human eye doesn't have that resolution. Even optical microscope is difficult to use to get this resolution. So you need to use an electron microscope. So once you put this under an electron microscope, that's what you see. Exactly like what this is depicted. So each of those regions is single crystalline. The neighboring region is also single crystalline. So I can count the number of single crystalline zones that are present there in this given area. And also look, the micrograph that I'm showing here is the top picture. So from the top of the, this block. So the microscope is imaging this surface. So if you're seeing this grain, right, it is not guaranteed that this grain also extends into the bulk with the same shape. It may taper off. It may grow into a bigger sized grain inside. So that's where sometimes the cross-sectional image is also very important. You start sectioning it and then go through the depth and find out, the surface structure is basically maintained throughout, or it's not maintained throughout, because depending on the thickness of this one, you always have this issue of nucleation leading to secondary growth, etc., etc. Okay, but ideally you expect what you see on the surface to be replicated in different depths of the polycrystalline bulk also. That means you start sectioning it, then you have to start sectioning it and look at the surface. So even though you see, if you section this one, you again get information about the cross section. So you section this and look at the surface, another section, look at the surface, then you have to stitch all that information to get information about the bulk of it. So that's a polycrystalline system, complicated. And the grain boundaries are the unwanted regions. They're defects basically, right? But today, we have this beautiful physics of defects. And if you start controlling these defects, you have a plethora of applications. And when you come to the last part of this, the form of solids, crystalline solid, polycrystalline solid, and completely non-crystalline amorphous. So there is no order among the crystallography. So that means there's no regular formation of the unit cell, right? So the long range order ceases to exist. So a very short range ordered system is called amorphous system, right? Probably you have order in very small pockets, in pockets of a few nanometers. Okay, that's why amorphous solids are called short range materials in terms of crystallographic correlation. Long range order is there, and here you can see the order exists in this form. Even if you take a metal, say again copper, you put it under a microscope, what you see is a structure like that. So a metallic system also has these grains and small regions separating different grains or domains. Well, what we call as grains and grain boundaries, in magnetic materials, we call them as domains and domain walls. In ferromagnetic system, you also have, there you talk about domains and domain walls. If it's a ferroelectric system, also you talk about domains and domain walls. So these domains and domain walls, again, play a very crucial role in controlling the physical properties. Yeah. So coming back to metals, metals also have this, the problem of existence of different zones, except that, the widths of these boundaries, what you see in metals and polycrystalline system ceramics, is quite different. As you can see here, these widths are very small. I mean, the scale is almost the same. The bar is not appearing here. But here you can clearly see, if you look at the, if I magnify this image, you'll find that the separation between two single crystalline zones is of the order of, few microns. It starts from half a micron to 1 and above microns. So that means what? I told you, if I'm doing a electrical conductivity measurement where I pass a current through the solid, the current has to find, it will go through the least resistive path only. Because at each point it has to surmount this barrier energy that is created by these grain boundaries. Okay, so if we need to do physical property studies on polycrystalline materials, if you don't have access to single crystals or thin films, the best option is to make sure that you prepare the polycrystalline material in a way that the grain boundary widths are minimized. So, well, you can go to higher temperature of sintering, that way the grain boundary widths can be reduced. But then as you increase the temperature, there may be a loss of certain elements from the polycrystalline bulk or matrix. That could be one of the issues. See, that also is shown here. The complete missing material, leaving a big void there. This is completely unwanted. But a polycrystalline system has all these associated problems. Okay. Now, in the case of metals, so whether we are dealing with metals or polycrystals, grain boundaries are always a big problem. The best example is if you take a piece of iron, we talk about the process of rusting. If you go to the beach side in Chennai, we have beautiful beaches here. The closest is the Besant Nagar beach. There are all these nice houses with metal gates, and all these gates are basically painted with anti-rust paints. And in spite of that, you still see some of these metal gates made of iron start rusting up after a few months. What is the process of rusting? So if you take a piece of metal, and especially in a place like Chennai, which is a humid place, Okay. What happens? So it's, I mentioned this yesterday that grain boundaries are diffusion inlets and outlets also. So that means if this block is made of yttrium barium copper oxide, which is a superconducting system that I talked about, oxygen plays a very crucial role in addition to the stoichiometry of other cations. And if you get this in polycrystalline form, there could be out diffusion of oxygen from the lattice through these grain boundaries. That means what? If I leave this polycrystalline bulk outside for some time, after a few weeks, you may see a depleted oxygen levels leading to changes in physical properties. So you do the electrical resistivity property today and leave it outside and then test it after a few months, a few weeks. If you start seeing a change in physical property, that means the material has been subjected to atmospheric degradation. This is one of the ways in which device quality materials are tested. You know, whether they're prone to atmospheric degradation or not. So suppose the components in our mobile phone are degrading as a function of time, they're supposed to work in all weather conditions. But if that is not the case, you have a problem. You may make a device out of your thin film, but then this thin film degrades as a function of temperature, and it has this severe atmospheric degradation problem. And if it is meant for use only in colder places, then you can't have a universal device. So this is a very, very important point that one needs to address when you're talking about looking at the technological aspects. So coming back to this, so all these iron gates, keep getting rusted. What is the process? What is happening there? So iron that is present there, Fe. See the grain boundaries. I said you have a unit cell. I'll go to the other picture. Okay, I don't have it here right now. So I have all these. Imagine this one is inside one of the grains, and the same structure is in the other grain, and the grain boundary that separates these two blocks is causing the trouble, because between two such blocks, the grain boundary, the defect, causes the termination of the atomic arrangement, right? So you may have loosely bound atoms there, and atoms that are loosely bound and sitting at the grain boundaries, loosely bound atoms are more reactive, they have more energy, so they're more reactive than these atoms that are bound into the solid. Because I can't take this as an individual atom and talk about its reactivity. No, because it is already formed into a solid, and so it has a cohesive energy. So to make it act as a single atom, first I need to break it out of this bonding. Then only I can make it react as a single atom. So the reactivity of these atoms sitting inside a solid and the atoms that form at the grain boundaries because of the termination of the regular periodic structure are different. So that is a problem basically. When the material is getting completely deteriorated, it's because of the fact that you have loosely bound atoms, they become more reactive. Same is the case here. So the iron gates that are made of iron, so if you take a piece of iron, leave it outside in this humid Chennai weather, what happens is after a few weeks, after a few months, you'll start seeing a formation of a brick red colored powder. It's very interesting. So what is that powder? So the loosely bound atoms at these grain boundaries, right? You have loosely bound iron atoms at the grain boundaries, they start reacting with the ambient atmosphere. That is, they take oxygen from the ambient air, right? And they get converted into iron oxide. That means it's a free reaction happening at room temperature. Now imagine if the same piece of iron has to be converted into iron oxide, you have to do a reaction at a certain temperature to make that happen. But here, because the reaction is happening at the atomic level, right? Well, this is also one of the bases why the reactions happen in nanoscale form much faster than reactions in the bulk form. Very interesting, right? This is a classic example. So all these loosely bound atoms, they're all in the atomic level, and their reactivity is much higher because they can easily capture oxygen from the atmosphere, and a room temperature reaction happens, leading to conversion of the grain boundary loosely bound iron atoms into iron oxide. So the so-called rust is nothing but Fe2O3, iron oxide. Iron oxide has different forms, magnetite, Fe3O4, Fe2O3, alpha Fe2O3, gamma Fe3O4. They're different forms. Some are magnetic, some are non-magnetic, but this rust is nothing but iron oxide. So in fact, if you leave a small piece in outside, it is sufficient to turn that small piece of iron into complete iron oxide over a period of time. Of course, it takes a few months. You must have seen this, iron rods that are not used for many months and years. You see a thick layer of iron oxide forming on it, right? That's why these are all chrome plated. Your bicycle handle is also basically made of iron, stainless steel, but it is further chrome plated because chromium doesn't get oxidized easily, right? Right. So how beautiful it is, so you don't want grain boundaries basically, right? They're problematic areas. And if you look at the top left picture here, this is what I showed you yesterday also. I said I can show you a piece of something like this, and I can call it a crystal. This so-called crystal is made of glass, and glass is not crystalline. Glass is completely amorphous. So when you see a piece of crystals like this and somebody asks you, oh, are these crystals? You can't say whether they're crystals or not, right? Of course, if you have a little experience, you can, if a small glass pane is broken, and of course, you need to be very careful about the sharp edges. If you have all those pieces in your hand, but then if a piece of, say, alumina crystals are taken in the other hand, they have different densities. You can find out that, yes, at least I can say that these two are different systems. But to look at a small shiny piece of something and say that it's a crystal is not easy. Okay. I'll come back here, but since I mentioned about glass and crystals, look at this beautiful example. We have plenty of sand in India. We have Marina Beach is the second longest in the world. It's nice to walk on the beach, and beach sands are very interesting. So this sand is SiO2, silicon dioxide. So, and it has a specific crystal structure. So if you take a beach sand and put it in an X-ray machine, you see the crystal structure of silicon dioxide. And of course, when you talk about glass is formed from silicon dioxide. So as long as beach sand is there is no problem for, making glass, right? So it's easy to make glass. How is glass made? You take silicon dioxide to its melting point above 1500 degrees centigrade, and then rapidly cool it, right? Rapid cooling forms glass. So this is not only the case with silicon dioxide. You take any material, you take zinc oxide, silicon carbide, barium titanate, lead titanate. You take any material and in its, this I would say is again the polycrystalline form. The silicon dioxide you get, so of course each grain is about each particle is, so to say, will be about a few tens of microns. You see, anything below 40 microns, our human eye cannot resolve, right? So these particles, when you take in your hand, you're able to see the, even if you spread them on the hand like this, you can see the particle size. Dust particles you can see. So the particle sizes are way above 50 microns and all the way up to some 200 microns, right? The coarser ones are much larger. I mean, the beach sands in some places, some parts of the world, right, are much finer than what you see in the Chennai beach. And it's much finer. Some of the European beach sands are much finer because they probably, these sand particles are continually bombarded against those big rocks before they come onto the shore. So they get pulverized. They get pulverized. So it's equivalent to taking these particles and then subjecting them to mechanical attrition. So you further reduce the particle size. That naturally happens in some part of the world. And in some parts of the world, it's very interesting that the same silicon dioxide, you see small crystallites, millimeter-sized crystallites. That means these beach sands are so pristine. There is also all the requirements for nucleation to happen between different particles, leading to the coalescence into larger particles. That means there is no external disturbance when this process is happening, but this takes several years, right? So it happens in those places, uninhabited places, where a process of a continual formation of small particles into larger particles can happen. So it's all about thin film growth, polycrystalline materials growth, single crystal growth is all about nucleation. And that happens naturally. You'll be surprised if you start studying the kinds of beach sands that you see in the world, coarser grains to very fine grains to crystallites. And some of these sand crystals are also colored. You know why? That's because you also have minerals in the sand that is swept from the sea. Under the sea, you have so many minerals. And over a period of time, there are also eruptions. And so these minerals get mixed up with water. They're thrown towards the shore. And then they can react with these sand particles. They can even get embedded and form doped silicon dioxide. In fact, if you walk on the Mahabalipuram and beyond Pondicherry side, on these pristine beaches where not many people frequent, you'll actually see streaks of minerals that are swept from the sea into the waters, onto the sand dunes. It's very interesting. Okay, so you take this is an example of silicon dioxide only. Any material on Earth, you take it to its melting point and rapidly cool it, you make a glass. Of course, the glass that we always refer to is the glass that we use in all these applications, right? My glass windows, glass panes, that is the glass we always talk about. That glass is made of silicon dioxide. And you must be wondering, the millions of tons of glass that is produced every day, where is the raw material for that? The raw material is silicon dioxide, right? That's why sand has such a great value. Okay, but the glassy form of any material is possible if you take it to its melting point. Zinc oxide, if you take barium titanate, which is a ferroelectric material. So you take barium titanate in its powder form or any form, you just take it to its melting point, right? Heat it to its melting point, quench it to room temperature. So what is happening during the quenching process? When I say quenching, it's rapid cooling. I melted the material. So silicon dioxide is in its molten state. That means its atoms are free floating, and by the process of removing the thermal energy, I'm not allowing those silicon dioxide atoms to form into a regular crystal lattice. Is it not? Because see, the molten state is a good platform for atoms to start moving towards their lattice positions like this. But then you need to give time for that. You need to give a lot of time for that. If you give a lot of time for this molten solid to settle down into a regular periodic area of atomic arrangement, right? Then you form a single crystal. So that's a tedious process, because to get a silicon dioxide crystal or any other crystal from the melt. So I said for thin film growth, for PVD technique, you need a solid or a molten source. But for single crystal growth, molten sources are a must. You must start from the melt. Otherwise, there is no crystal growth. So you take the material in a polycrystalline material and just take it to its melting point. So you have it in a bowl or a crucible. This crucible is taken to the melting point of the material. So you see the melt of the material. And if the melt is rapidly cooled to room temperature, that's it. It forms into a glass. So the term glass means non-crystalline, amorphous. That means the glassy form has no crystallinity. That's the meaning of glass. Glass doesn't mean, as I told you, the glass that we use in our day-to-day lives, right? Glass means non-crystalline, because we can't afford to have these window glasses made of crystalline silicon dioxide. Because that process is a long process and it's very expensive. Okay, because
Sir, I have a doubt, sir.
yes,
Tanvir. Sir, so does that mean that silicon dioxide has more material strength than glass because silicon dioxide is a crystal?
yes, yes.
Okay.
Silicon dioxide. See, the material strength. You also need not think that the moment. Okay, the answer is yes and no, because if a given material is obtained in its amorphous form, non-crystalline form, and crystalline form, right? We need not think that the crystalline form always will have a higher strength. You know why? This is an interesting question also. In some cases, I can give you some examples. The glassy form may be more strong compared to its crystalline form, right? Even though you get the required physical properties there, because crystalline form, once you form the material into a given crystalline form, imagine you take a crystal, we can also break a crystal, right? I can break glass, is it not? And in a similar way, I can break a crystal also.
Yes, sir.
So when you break a crystal, the breaking happens along a particular crystallographic axis, right? Because so you take this crystal, for example, okay? So if I go through different planes on this crystal that I show there, of course, this is a combination of a large number of unit cells I put in there. So there are certain planes along which there will be less number of atoms. And in certain planes, there will be more number of atoms. So crystal, when you break, typically, it cleaves. It cleaves means it breaks along a certain crystallographic axis. You see a nice cut along a certain crystal. Actually, you can identify the crystallographic axis. Actually, you see, this is this crystal, the naturally formed crystal. It's this plane is an identifiable plane. So that means it has a cleavable crystallographic axis along that plane. And since that kind of directionality is not there in the case of glassy material, sometimes glassy materials can be more strong. You understand?
Yes, sir.
Yeah. So that's why in metallic systems now they talk about bulk metallic glasses, where they want they subject the metal to the same process of melting and quenching. So to make the amorphous nature, so that metallic bonds are already non-directional, right? That non-directionality brings strength into the system. Okay,
Okay, sir.
All right. So this is it. Silicon dioxide melted, rapidly cool it, you get glass. Well, so rapid cooling in the sense, if I have silicon dioxide in a crucible and inside a furnace, I take the crucible outside the furnace. You don't take it down to the room temperature immediately. If from 1500 degrees centigrade, for the crucible and the molten silicon dioxide to attain room temperature, it will take several hours, based on the Newton's laws of cooling. The initial drop in temperature will be very rapid, and then it goes in an exponential way. So if you really want to achieve, quenching, where you don't want to give any time for the atoms to settle down to their lattice positions, you can quench them, melt into ice, 0 degrees centigrade. Boom, you drop it, or into liquid nitrogen, right? Ice is the best example, affordable. And now I have a liquid nitrogen bath. I drop this melt into a liquid nitrogen bath. So I'm not allowing any time for the melt to naturally cool down to room temperature. Natural cooling from 1500 degrees centigrade takes about anywhere from 1 to 1.5 hours. And if you don't want to give that much amount, so that time is also sufficient for atoms to settle down to their lattice positions. At least some form of crystallization happens, right? But if you don't want to give that even that amount of time, just quench it. That is the actual definition of quenching. Quenching it to ice temperature or liquid nitrogen temperature. Okay. But glass has various applications. The non-crystalline form of silicon dioxide. So when I said materials obtained in amorphous form, it doesn't mean that they're not good for applications. The fiber optic communication technology is all based on silicon dioxide coated fibers. You need to get that total internal reflection, and the glassy form of silicon dioxide helps in maintaining the flexibility of this is what I'm telling. So if you have a crystalline silicon dioxide coated inside these flexible fibers, they'll break, they'll chip off, right? So the glassy form helps there. Yeah. So the crystal growth form is much more complicated, as I told you. The same melt you have to deal with in a much more sophisticated way. I just want to spend a few minutes because you need to know what is crystal growth. One of the well-known methods is called the Czochralski method. It's called the CZ method, Czochralski, where you see that you start with silicon dioxide, and I can process it and get silicon in the form of these small silicon ingots, polycrystalline silicon. So this is a raw material that is required to grow silicon wafers, the wafers that we get. But the process involved is, it's a lot of process. First of all, you process silicon dioxide to get silicon. And again, our silicon electronics, even though people are looking at alternatives have to be worked out and looked at. There are alternatives, but then the microelectronics industry cannot do away with silicon. And so the new technologies basically have to be integrated with silicon-based technologies. That's how it's going to go. Even though even Intel is thinking of oxide-based materials for switching, and the oxide materials offer a plethora of applications, right? So they want to integrate all these oxide carbide-based materials to integrate with silicon-based electronics. But the glass formation and making of silicon wafers will not be a problem because the raw material is just bead sand. From this, I can make a glass, and I can also make silicon dioxide in its most crystalline form. So I get polycrystalline silicon ingots. That is a raw material for me, and I take it to its melting point, melt it. But then here it's simple. Just rapid cooling gives me glass. But then this is a tedious process of slow cooling. And how it is done is there will be a small seed there initially. The seed itself is silicon dioxide. Imagine you look at this. you know, the seed is actually there. So on the seed, the nucleation of new silicon crystal happens, and the seed is pulled up, right? This is, the rotation is happening, and slowly it starts going up, and this leads to, you know, cooling of that melt. You're taking the molten part of the silicon that forms into a solid beneath the silicon crystal, and when you start pulling it up, the temperature gradient is created, and these temperature gradients, sometimes the temperature, the cooling rates have to be as low as 1 degree per hour, 0.5 degrees per hour, and there should not be any variation in the you know, the temperature, the rate of cooling. If there are variations in the temperature, that can lead to strains in the single crystal that is formed there. That's why I said single crystal growth is a very expensive and also tedious process, because you make this 5 feet long. Well, one interesting thing is the microelectronics industry survives because silicon can be made into these large balls of big crystals. No, this could be as long as 5 feet, and of course the technology is based on 8-inch and 12-inch wafers, and the process allows this to happen. But one such ingot, you imagine how much of raw material is required. Even though you get it from silicon dioxide, a lot of raw material is required, right? You melt it, you slow cool it, Czechoslovakia process, and then you slice it. First of all, it is tested by X-ray diffractometers to see the quality on the entire length, and then you find a crystallographic axis and you start cutting them. Then you get then only you get a wafer like this. Wafer that is basically, see, it's so what we see now finally in this form, right? Shiny silicon dioxide, silicon wafer. Is that, yeah, I see how shiny it is. It's cut from one of those wafers. So the cutting technology itself is quite complicated, because mechanical cutting wastes a lot of this material. So these days, lasers are used to cut so that to minimize the waste. And then the crystal, so it's a crystal there. What you see here is a crystal, and this has to be cut along a particular direction. Now this is the 100 silicon cut crystal. That means the top surface is 100 plane, right? So perpendicular to that is a 100 direction, right? So that's how silicon wafers are grown. I can use this wafer, the silicon wafer, to grow thin films on top of it, and then you go for device fabrication. You see how many steps are involved, right? Right from understanding the quality and nature of silicon itself, there's so many important things involved. I think I'll stop there. I think I can. Okay. Yeah, I'll stop there. Yeah, just to quickly tell you. So if you have a single grain here, like in a polycrystalline system, I said that grain is a single crystal where you have periodic arrangement of unit cells in the entire volume of the grain. That's what it is. And that is a unit cell. And that periodic arrangement terminates at the grain boundary, and then it again happens on the other side. But the interesting thing here is, if these unit cells are all arranged in a particular fashion, in the neighboring grain, the crystallographic orientation may be in a different direction, right? So if it is a cubic lattice, it's no problem. But for other lattices, so if I identify, say, AB plane in this direction, so the AB plane will be in that direction, and so on. Okay. So these are the issues with respect to polycrystalline materials. Okay, so I'll stop there. I'll see you again on Monday. And probably next week we'll have all the 4 classes. So I'll send out the links. I'll send out all the information of my presentations and these recordings. Um, I'll do it during this weekend. And yeah, I'll also, from probably after next week's classes, I'll give some assignments so that you'll start reading stuff related to these topics. And now it's good for you to have a better understanding that way. Okay, any questions you have? You have your